For this lesson, we're going to be taking a look at what is probably a new idea for many of you, which is the idea of a family of quadratic relations. The graph of a quadratic relation, as you should know, is a parabola. And when we take a look at the graph, we see certain characteristics. Some of the common characteristics that we might see are things like we might see zeros, we might see the vertex of the parabola, we might take a look at the y-intercept. It is certainly possible to have parabolas which are different from each other, but may have some of these characteristics in common. And when you have two or more parabolas or two or more quadratic relations which share a common characteristic, we group those together and they're called a family of quadratics. Now you can have a family based on pretty much any characteristic you want, but the characteristics that we're generally interested in for a quadratic are the ones that I listed at the beginning. So zeros, vertex, x-intercept. If we take a look at these examples that I have below, these first two quadratic relations quite obviously have the same zeros. So if you're comfortable with the idea of factored form, this first relation has a 0 at x equals 2 and x equals negative 5. It doesn't matter the order that they appear. This also is x equals 2 and x equals negative 5. But now I've thrown a standard form into the mix, and that may complicate things a bit. And so at this point, I need you to make note of the fact that they don't have to be in the same form. One of the things that we've developed in our lessons and discussions about quadratic relations is how to move between forms. In this case, standard form. To move from standard form to factored form, we perform what's known as factoring. And in this case, if we factor this, what are two numbers that multiply to negative 10 and add to positive 3? And those numbers are x plus 5 and x minus 2. The numbers are 5 and negative 2. And so as you can see, we end up with the same factors, and these have the same zeros. So in order to check this, if you can convert, or if you're given all of your equations or your relations in the same form, then you can find out pretty quickly whether or not they are in the same family. Similar idea over here. I've got the same y-intercepts for equation 1 and equation 2. Both are at negative 10. But the third quadratic relation is in vertex form. So if I wanted to convert this into standard form, I would have to, in this case, expand and simplify. And in this case, if I did that, I would actually end up with negative 10 as the y-intercept. So you do need to be able to adapt to that, to the idea that you're generally not going to always have them in the same form. If these are given to you in a graphical form, it becomes quite trivial because all you have to do is look for some common characteristic that they all possess. So let's focus on the algebra, because as you can see here, if I show you the graph, here's an example of a family of quadratics that have the defining characteristic is the same zeros. So you can see that they cross at the same zeros, in this case negative 3 and positive 2. Here is a family with the same vertex. All of the parabolas have a vertex at negative 2 and it looks like positive 5. And then finally, a little bit harder to see here, we have a bunch of parabolas and they all have the same y-intercept here. In this case, this intercept is at negative 5. And I know it's a bit of a jumble, but if you take a look, some of these parabolas, for example, I can actually tell quite clearly this parabola, here's its vertex. So seeing all of these lines just going in different directions, you might think, well, isn't that the vertex as well being common? But it's not. The vertex of different parabolas is at different locations. There's a vertex of another one of the parabolas. But the thing that they all have in common, the point that they all have in common, is the y-intercept. So if it's a diagram, if you've got the graphs, particularly if they're computer generated graphs, if they're high quality, then you can pick out the families relatively easily. But what about algebra? Now in this case, I've made it even more difficult. I'm actually giving you one of the relations in each of the forms: factored form, vertex form, and standard form. Any one of these forms is quite useful for determining one of the features or one of the characteristics. For example, factored form is useful for telling us the zeros. Vertex form, not surprisingly, is useful for telling us the vertex. And standard form is useful for telling us the y-intercept. So the question then becomes, well, how can I work between these? How can I test for the same vertex or the same zeros or the y-intercept? What's the easiest way to do this? And this word easiest can actually take on a double meaning, so I'm going to explore both. The most straightforward way to do this, as I discuss here, the most straightforward way to do this is just to change all relations to the same form. We've talked about if we have standard form and we have vertex form and we have factored form, there are methods for switching between these forms. You can move between these forms if your algebra skills are good and you've learned these methods. For example, standard form to vertex form is completing the square. Standard form to factored form is factoring. Factored form to vertex form is making use of some form of symmetry. Vertex form to factored form is finding the zeros, etc. Now, I've covered this in previous lessons, and you should have covered this in your previous courses as well. But there actually is. So this is, when I say easiest, well, this is not necessarily algebraically easiest, but this is the most straightforward way to do it. So if you're trying to test for a family of the same vertex, change everything to vertex form. But there's actually an easier way from an arithmetic and certainly from a speed point of view, and that is to actually focus on the idea of those key characteristics. And in particular, I want to think about it in terms of key points, and then we're going to test those key points in all of the relations using substitution. So what do I mean by the key points? Well, in the case of a y-intercept, the way you find a y-intercept is you set your x value to 0, and then you see what's left over. So setting the x value to 0 for each of your relations should give the same y-intercept. So really that's what we want to know. Are the y-intercepts going to be the same? For zeros, if you can find the zeros for one relation, remember that a 0 is a point. So you're going to have your first 0 is going to occur at x1, y1, and your second 0, a second point, is going to be at x2, y2. So we can sub x1 and x2 into all of the relations, and I better get y1 and y2. But even more significant here is the fact that the y1 and y2, because we're looking for zeros, well, that's actually going to be 0. So we have to test and make sure that we always get y equals 0. And with a vertex is at hk, which is just the x coordinate and the y coordinate. So if I sub in this x coordinate into each relation, I should get this y coordinate from each relation. Now that's a lot to just try to take in terms of text. So let's go ahead and take a look at what this will look like in practice. So here are those same three relations, one in factored form, one in vertex form, and one in standard form. Now I think the easiest place to start is actually to test for the y-intercept. Because if you happen to have something in standard form, it's right there, it's easy to read. So in this case, I'm going to say the y-intercept is at 0, 8, because that is the y-intercept for relation number 3. Actually, maybe instead of numbering these, maybe I'll label them with letters. I think that might be clearer in this case. So relation A, relation B, relation C. So the y-intercept of relation C is at 0, 8. So now what happens if I take a look at relation B and I set x equal to 0? because that's this value. So in relation B, I get y equals x equals 0 gives me 3, 0 minus 2, all squared plus 16, which gives me 2 squared is 4, 3 times 4 is 12 plus 16, and that gives me 28. And as we can see, that is not the same y-intercept. This is the y-intercept for relation B, but it certainly doesn't match the relationship for relation, and that was relation C. So I think I'm going to just go ahead and change this to relation C. And we could stop here. It's obviously not a family of y-intercepts, but let's go ahead and take a look at relation A anyway. Y equals, and I'm setting x equal to 0, so that's -1 in front. That's this part. And then it's going to be 0 minus 6 and 0 plus 2. And that gives me negative times a negative times a positive. So it's going to be positive 12. And once again, we didn't need to do this, but it depends on the order you do this. So in this case, none of them have the same y-intercept. So they're not a family of y-intercepts. And you could, for completeness, oh, let's change the color of that. You could say, therefore, not a family of y-intercepts. Okay, now what's next? It really depends on what you think is easier. I'm just going to go to A now. I think A and B are quite interchangeable, but in A, from A, what are my zeros? From A, I have zeros at, and let's just make sure I get them right, 6, 0. That's one of the zeros. And -2, 0. So now that I've said it, I said they're interchangeable, but doing these zeros is actually the one I think is the most work, because you have to test both of these points. So when I test relationship B, I have to sub 6, or I have to sub x equals 6. And I have to sub x equals -2. I have to do both of these substitutions into that. So let's take a look at relationship B again. If I can get this screen to move up. 3 times x minus 2 all squared plus 16. So y equals 3 times x minus 2 all squared plus 16. 3 times 6 minus 2 all squared plus 16. Remember, all we need this to be is 0. So even if it becomes obvious that it won't be 0, we can actually stop there, but I'm going to finish it. 6 minus 2 is 4. 4 squared is 16. 3 times 16 is 48, plus another 16, which is obviously not 0. You could stop here if you wanted to, but we could go further. So 48 plus 16 is 64. It is obviously not true, and in this case, I can just go ahead and stop. It is not a family of the same zeros. And so with this one, I'm not going to carry on. But let's say this was correct, then I would have to check this one. And if this one was correct, I would have to go on to relation C. All right, now let's finish this up. And I've got, now I need to do the vertex. The vertex is at 2, 16. And that's coming from relationship B. It says there's a vertex at 2, 16. So I'm going to sub this x and I'm going to look for this y. So what does relation A look like when I sub this in? I get y equals, and I believe it was negative x minus 6, x plus 2. So x minus 6, x plus 2, negative, and now instead of x minus 6, I'm going to do 2 minus 6, and instead of x plus 2, I'm going to do 2 plus 2, and I end up with negative bracket -4 bracket +4, negative negative positive gives me +16. Oh, hey, that is a correct result. So that means that so far they're in the same family. So let's check relationship C, which was the one that was in standard form. Negative 2x squared plus 8x plus 8. Negative 2x squared plus 8x plus 8. And so I go ahead and sub in x equals 2. That gives me negative 2, 2 squared, plus 8 times 2, plus 8. 2 squared is 4. Negative 2 times 4 is negative 8. Plus 16 plus 8. Negative 8 plus 8 is 0, leaving me positive 16. And in this case, that also matches. So therefore, it is a family with common vertex. Okay, and so we have found our family. And up here we could have added it is not common. And what were we testing up here? I believe we were testing zeros. So this one is not common zeros. So there can be quite a bit of work involved here, but believe me when I say this is still less work than rearranging all of these equations into the same form, because you would have to do those rearrangements for each of the forms to test it, unless you got lucky with your first try. Okay, what's another kind of question you might see related to families? This one doesn't have you testing families, but it has you doing some of the algebra related to it. So this one tells you we have a quadratic relation in standard form is what we want. But the information we're given is that the quadratic relation has these roots. But we have it with these roots but passing through two different points. So this would be the same family of roots or zeros, right? That's when we talk about roots, we're talking about zeros. So this is a family of roots because they have these things in common. So in general, when we talk about roots and zeros, normally we will start with factored form. So the general form of a factored form relation is some leading coefficient x minus s, x minus t, where s and t are the roots. But we know the roots, so we can actually rewrite this as a bracket x minus, but now instead of s, I'm actually going to put 1 plus the square root of 5. And then x minus, but instead of t, I'm going to put 1 minus the square root of 5. I'm trying to use color there to keep it clear. Now I'm going to simplify. And you're going to see something very interesting that happens here, and it happens quite commonly. But in this case, there's a certain symmetry to these roots. So x minus 1, and this negative times this positive root 5 becomes minus root 5. And then we have x minus 1, negative times 1 is negative 1, and negative times negative root 5 is positive root 5. At this point in time, you could use what's known as the distributive property. So you could take this x times this x, and then times the negative 1, and then times the root 5. And then you could do this negative 1 times this x, this negative 1 times this negative 1, this negative 1 times this root 5, and finally you could finish with these multiplications. And as you can see, I get quite a mess here just drawing these with lines, but I also end up with a lot of terms. In fact, I'm going to end up with 9 terms that I have to work through there. Now, you can't get away from the algebra, at least to some extent, but you can make your life a little bit easier if you recognize that this piece is the same as this piece now, and this piece is the same as this piece. So what we actually have here is the form P minus Q multiplied by P plus Q. We have a difference of square situation. So if this was P and Q, this would be equal to A bracket p squared minus q squared. But of course, we don't have p and q. What we have is a bracket, and p squared would actually be x minus 1 all squared minus q squared, which is going to be the square root of 5 all squared. And although this still requires some algebra, it's significantly easier than the algebra that we were looking at having to do before, just by virtue of not having nearly so many terms to keep track of. X minus 1 all squared is x squared minus 2x plus 1. And then root 5 all squared is just 5. So that's going to be minus 5. And I end up with y equals a x squared minus 2x minus 4. So that is our first pass at this, but we still don't know what this a value is. And now, this is a lot of work I've done so far. I'm just now ready to actually address a, which gave us the point 25. In order to solve for a, I sub this in. So this is my x and this is my y. So instead of y, I'm going to sub in my value 5. Why do I keep doing this? Let's try it one more time to get the colors right. 5 equals, I don't know what a is, bracket, but instead of x squared, I'm going to put in 5 squared minus 2, and instead of x, I'm going to put, did I just make a mistake there? I did. My apologies. My x value is 2. So let's try that again. Instead of x squared, I'm going to put 2 squared minus 2 times, and instead of x, I'm going to put 2 and minus 4. And so I get 5 equals a bracket, 2 squared is 4, minus 2 squared is minus another 4, minus 4. And all of these things together, 4 minus 4 is 0, so I end up with 5 equals negative 4a, or a equals negative 5 over 4. So this one has an equation, y equals negative 5 over 4 multiplied by x squared minus 2x minus 4. And what I really should do now, because the question does ask for it in standard form, is I have to expand out this bracket. So I end up with y equals negative 5 over 4 x squared. Negative times a negative is positive, but this is, actually I'm going to just take my time here. So this is going to be 5 times 2x over 4, and then the negative times a negative is positive 5 times 4 over 4. And the reason I said I'll take my time there is because there's some extra common factors. 2 goes into 2 once and 2 goes into 4 twice. 4 goes into 4 once and 4 goes into 4 once. And so my final answer here is y equals negative 5 over 4 x squared. And this is just plus 5x over 2, and this one is just plus 5. And so that is the answer to part A. We have a part B to do for the other equation from the same family. And so in part B, it gave us the point, I believe the point was 210. I'm going to go back to the top and check that. 210, and the equation that we're subbing into is a x squared minus 2x minus 4. Y equals a x squared minus 2x minus 4. And so I sub in now. I'm not going to switch colors because that caused me to go off the rails before. Y equals 10, a, and now the x coordinate squared. Well, actually, this ends up being the same as what we had before. So x squared is 4, minus 2 times x is minus 4, because in this case, the points actually have the same x coordinates. That's just how I chose them. And so now I end up with 10 equals, and this is negative 4a. So a is equal to negative 10 over 4, which is the same as negative 5 over 2. And now I need to apply that to the overall quadratic, x squared minus 2x minus 4, and expand it. Negative 5 over 2x squared plus 5x plus 10. And so that is my second equation. And these two equations don't look a great deal alike. They have some common features to each other, but in just looking at the two of them in standard form, you wouldn't know that they have the same zeros. Okay, and that's it for this lesson. The assigned work is a worksheet that's located on the website.